going to ever force you to turn on your video, but it's so nice when you do. I so like looking at your faces. It so helps. It's just really, really, so nothing, no forcing, no anything, but it's nice when you turn on video. So, all right, let's see. Homework questions. No extra credit. No, you cannot have extra credit for turning on your video. Although that might work in my cryptography class. Okay, great. Yes, no, okay, here we go. Anything for homework questions? What have I ever done that would make you feel like I'm that nice of a math professor? Ever. Anything for homework questions? Or we can do these on Monday also.
You canceled chapter 3.
I did, that's true, but that was more due to the global pandemic than me being a nice math professor. So, you know, occasionally things happen that are appreciated. Anything for homework questions? Due next Friday. No? Good? Happy? Okay. All right, then. Today is not a lot of linear algebra, or not a lot of differential equations. Today is a lot of linear algebra. So we have done differential systems of differential equations with, we played around with it and it was terrible and you disliked it, and I don't blame you. In section 5.1, there was no systematic method. And then in section 5.2, we said, oh yeah, we can make this a little bit more systematic. Let's do that. At this point, all we've had, except maybe one on the homework, is still one independent variable. Remember, 2 independent variables is partial differential equations. We're not doing that. 1 independent variable, but 2 dependent variables. We haven't gotten much beyond that. Maybe a little bit with 3 on the homework, but mostly all 2 in class. And if we want to get bigger than that, which we do, we want to get to bigger systems, then we need some even more systematic methods. And for that, we have to talk about matrices. So that is section 5.3. Matrices and systems of differential equations. Matrices and systems of differential equations from 5.3. Today, mostly all matrices. Since linear algebra is not a prerequisite for this class, I'm not assuming that you've taken linear algebra. I know some of you have, and actually I'm gonna stop sharing my screen just for a minute. How many people have taken linear algebra? Remind me. Yes, maybe, okay, half-ish, somewhere in there. Okay, so I am not going to tell you to stop listening to me because you're still going to need the stuff from today, but this should be a nice, good review for you, hopefully. If you haven't, then this is going to be a really, really quick introduction to the basics of matrices and linear algebra. And if it is interesting, we just happen to offer linear algebra next fall, Monday, Tuesday, Wednesday, Friday, 8 a.m., and I'm pretty sure I'm teaching it. So there we go. All right, matrix notation. We've kind of done this already with the 2x2 matrix, but we haven't made it systematic. So it is an M by N array of numbers. M is the number of rows. And N is the number of columns. So M by N array of numbers, M is the number of rows, N is the number of columns. The way we usually write this is with subscripts. So we'll do capital letters for matrices, right? We're gonna start with A11 in the top left-hand corner. So we do capital letters for the whole matrix itself and lowercase letters for all of the entries or components inside. And then if I'm reading across, the second component, second subscript represents the column. So my next one reading across would be A12. If I keep reading across, we'll have A13, and then a bunch of dots. Since there are N columns, I need to go to A1N. n columns, so I need to go to A1n. We'll do one more row and then we'll do some dots going down also. So A21, A22, A23, bunch of dots, A2n, okay? And then we can do dots for the rows and also, and jump to the last one. So there are m rows. This last one is going to be AM1, AM2, AM3, bunch of dots, AMN. If you want to do shorthand notation, so this matrix is kind of like when you have a summation and you write all of the pieces out with the plus dot 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 in the middle, or you can use the sigma notation. We can also use shorthand notation here. So we can say that this is A sub ij, where I is 1, 2, all the way through m, and j is 1, 2, all the way through n. We won't always write these ij subscripts. A lot of the times we will just assume that we know how many rows and how many columns there are, but A sub ij is your shorthand matrix if you don't want to write your matrix out with a bunch of dots. Okay, couple of special matrices. Oh, by the way, plural of matrix. If you say matrices, you are going to make me cry. Don't say matrices. Matrices is the plural. Matrices. Matrices makes you sound like you don't know what you're talking about. And grates on my ears. The zero matrix is denoted by a capital 0. That sounds stupid. A big 0, make a big 0. And it is the matrix with all 0 entries. So that's the 0 matrix. A is equal to B. So 2 matrices are equal. A is equal to B if A sub ij equals B sub ij for all I and j. And again, this would be where I goes from 1 to m, where j goes from 1 to n. So 2 matrices are equal if all of their components are equal. Adding and subtracting matrices is super easy. So adding and subtracting matrices, and we've already sort of done this, we just haven't talked about it. So adding and subtracting matrices is no big deal. The first requirement is they need to be the same size. And then you add or subtract the individual components. So they have to be the same size, and you add or subtract the individual components. Remember, the components are the little numbers inside the matrix. Add or subtract the individual components. I don't think I need to do an example with adding and subtracting matrices. Do I need to do an example with adding and subtracting matrices? Even if you hadn't had linear algebra before, I think we're okay. We're okay. All right, I'm getting nods, yes, okay. Scalar multiplication. Oh, and my notation here, I should say. So it's A plus or minus B, right? 2 matrices added or subtracted, A plus or minus B. So scalar multiplication is multiplying a matrix by a scalar. Remember, a scalar is a fancy word for a number. So multiplying a matrix by a scalar. So its notation would be K times capital A. Remember, we usually use lowercase letters for numbers. So K times capital A. And then all you do is multiply each component by lowercase k. So again, that's easy, no big deal. Scalar multiplication, just a scalar times a matrix. All you got to do is multiply each component of the matrix by k. Easy, no problem. I don't think I need to do an example of this either. Just multiply k through the matrix, kind of, sort of. Okay, couple of properties of matrices, and then we will get to matrix multiplication, which is the fun part. So, properties of matrices. This, I think, is going to be part 1. I don't know if there are 2 or 3 parts, but part 1 for properties of matrices. First of all, A plus the 0 matrix is equal to A. A plus the 0 matrix is equal to A. If you were in class, if you could respond better, I would ask you what property this is. It doesn't work so well to ask you here. So this is the additive identity. 0 is the additive identity matrix. You add 0 to anything, you get the anything. Secondly, A plus B is equal to B plus A. That's my second. A plus B is equal to B plus A. So matrix addition is commutative. Matrix addition is commutative. Thirdly, A plus in parentheses B plus C. I can move the parentheses. A plus B plus C, and that's matrix addition is associative. Matrix addition is associative. We can do K times A plus B, and I can distribute the scalar. So that's K times A plus K times B. So this is scalar multiplication, distributes over matrix addition. Scalar multiplication distributes over matrix addition. And then last, we can do K plus L times A is KA plus LA. K plus L, it's an L, sorry, it doesn't look like an L. K plus L times A is K times A plus L times A. This technically doesn't have a name because my operation has changed. And anyone who's taken me for Calc 3 or for linear algebra, or if you've taken abstract algebra, you've heard me talk a lot about this. The operation over here is addition of 2 scalars, operation on the left-hand side. Operation on the right-hand side is addition of 2 matrices. So this kind of sort of looks like the distributive property, but not exactly, because my operation isn't the same on both sides of the equation. Okay? All right, that's a good spot to pause, take breaks, maybe able to see all of you again. Give me a thumbs up. Yes, tell me we are doing good at this point in time, even though I have no examples. Okay, cool. If you take linear algebra, we prove a lot of these properties. So if you take linear algebra, we will actually prove they're all equations. So we start on one side of the equation, we work our way to the other side of the equation. We do a lot of proofs here. So that's what's happening with linear algebra. All right,